You're going to like today. Today is some good stuff. It's going to be one of those things where we get done and you go, that was a little too easy. Is that all we're doing today? Well, if you pay attention, yes, it will be that easy, and it'll be what we're doing today. But here's the deal. You know what happens when things are too easy for us? We forget them. What's the equation for direct variation? Who said that? Dominic? Y equals kx? He remembered it. That was so easy for us. In 2-2, y equals kx was so easy for us. You came back the next day, there was maybe like one homework question. It was like, we got this. But our brain didn't retain it because our brain said, I don't need to remember this. This is too easy. Try and avoid that today, okay? Think about each individual step, and then that won't happen. As we go through this, you think, okay, I start here, then I do this, then I do this. Then your brain will start to retain some of that because we got a weekend coming up. 2 days of not doing anything. No yay. You should come in on Saturday and Sunday. We'll remember everything. Absolute value functions and graphs. We're going to graph absolute value. And I want to remind everybody that when we're talking parent functions, that's the most basic absolute value function we can get. No bells and whistles. Doesn't have any numbers in front, doesn't have any numbers in back, doesn't have anything tacked inside the absolute value. So our objective is to graph those absolute value functions. And because it's a function, we're going to call it f of x equals the absolute value of x. But you could call it g of x, p of x, whatever you want to call it. It's just, for some reason, when we talk about functions, f, g, and h are the three most used. It's like that part of the alphabet gets used for that. Now, here's something super cool about these. They're a V. Look at that. Absolute value graphs are V's, but they go on forever. You know, that's why we have to be so careful about arrows. So, absolute value is going to look like that. A little something like that. Cool. So it says it's symmetric about a vertical line called the axis of symmetry. So memory make time. Symmetric, symmetric, symmetric. That means if I fold it over, I get the exact same thing on both sides. Oh, yeah, I can see that. If I fold it over, I'm going to get the exact same thing on the other side. So it's symmetric. And that line down the middle is either called the line of symmetry or the axis of symmetry. Your book calls it the axis of symmetry. But that's when we fold it over. It has a single maximum point or a single minimum point. Hold the presses. Bless you. This one. This is going up forever. So if it's going to keep going up, it can't have a maximum. But it definitely has a lowest point right here. So this one would have a minimum. Definitely would have a minimum. So what would it have to look like for it to have a maximum? Think about it for a minute. What would we need to do that? So instead of having a minimum, it would have a maximum. Flip it over. Ooh, that arrow got a little carried away there. This one now has a max. The red one, does it have a minimum? No. Arrows are saying, hey, we're going to go down forever. That's why they used the or word. You know, you don't get both, one or the other. And the name for the little point is the same as it's always been, which is vertex. You know, when we talk about triangles, we'll say the vertices are A, B, and C, and that's what we do. So, the vertex. Too many phones out there. I might need to start a phone collection. Put them away. Put them away. All right, we're learning here. Slope of the right side of our V is 1. How are we supposed to know that? Just looking at that. Well, how many absolute values of x do you see? That's how we're supposed to know that. The number in front of that is a 1. That's the slope of the right side of this graph. So it's that whole symmetry equal but opposite thing. It just makes sense that this side is going to be a negative 1. Here we'd go up 1 and over 1, and here we'd go up 1 and left 1. It'll work. So the right side of the branch, positive 1. Again, this is just for the absolute value of x. The left branch, negative 1. You know slope. You asked me for a couple of problems today where I graphed a couple lines with slope-intercept. You know slope. So now, absolute value parent function. F of x equals the absolute value of x. You think absolute value, that is the distance something is from 0. Oh, that's right. You can't have negatives. It has to be positive. So, if I put a negative 3 and negative 3, negative 2 and 2, negative 1 and 1, 0, 0, 1, 1, 2, 2, 3, 3. Okay, makes perfect sense. When you graph that, you get this V. 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. And backwards, we've got our negative 1, 1, negative 2, 2, negative 3, 3. Makes perfect sense. Yeah, that's the axis of symmetry. And the axis of symmetry is the y-axis, but its mathematical equation is the line x equals 0. Here's why. When we draw the y-axis, we have to karate chop the x-axis. That's how it gets its name. And we karate chop it right at 0. So it's x equals 0. Our vertex, 0, 0. Makes perfect sense from this nice little table over here. That's that lowest spot, that minimum. But then, we look at that. Do we have to know that, Cedar Home? What on earth is that? Yes and no. Here's what we need to know. We need to know that that just explains what happened in our table. That's all it does. We have our own language in math. I call it math speak. And our language can be a little bit tough at sometimes. This is called a piecewise function, and here's why. And Slade's going to close that cover, so I'm sure he's paying attention. Right over here, we see that we have a right side to this graph. We also see the left side is different than the right side. So what a piecewise function does is it says, do this stuff over here, but do this stuff on this piece. So it kind of separates it into two different pieces and talks about it. Now, I'm going to talk you through this translation of this math speak. It says, absolute value of x is x when x is greater than or equal to 0. Okay. You put a 1 into absolute value, what do you get back? Do you seriously not know this? What's the absolute value of 1? 1. Absolute value of 2?
2.
Did your numbers change when you put them into absolute value?
No.
So that's what this says. If you put in positive numbers, you're just going to get the number back. Now, this one says something different happens when you put negative numbers in. What's the absolute value of negative 4?
4.
Absolute value of negative 6?
6.
So you really just took the opposite of your negative. That's what this says. So this is just a way that we write things in math to show here's one side of the graph, here's another side of the graph, and break it into pieces. Now, why does it have to be that tough? Because in calculus, you need to be able to split it up that way to do some of the things that you do in calculus. But we're not going to write that, and we're not going to think that as we work through this. We're going to think much more basic than that. So down here, it says, we're ready to start talking about this stuff already. Well, how can that be? What is the graph of the absolute value function of that? How is this graph different from the graph of the parent function, which is this? Well, this is where we're going to color code. Because we're going to say, you know what? I know what that one looks like. I know what the parent looks like. It's a big V. Got this. So 0, 0, 1, 1, 2, 2, 3, 3, blah, 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 all the way up. And negative 1, 1, big V. There's my parent. Here's what I can't do with that. I can't make it solid. I can make it dashed or dotted because that's a helper. That's not my final graph. This is just a helper. So I'm going to put some dashes on here to remember color coding. This is just y equals the absolute value of x. That's all that one is. All that's happening. Normal. Now, if you wanted to do this as far as slope goes, you'd start here and you'd say, okay, I go up one and over one, up one and over one, up one and over one. You get the exact same dot we just got. And then you go backwards and say, I'll go up one and left one and up two and left two, up three and left three. You know, you get it however you need to get it, but you need that perfect beat. Now I look at the one I underline in red. And I remember what we did yesterday, and I think, I wonder, can I just use those transformations that I talked about yesterday? Well, they wouldn't have been the day before this lesson. What does a minus 4 do in the back? A couple people are doing this. I do read this. Just that much, though. Down 4. So we need to translate this graph down 4. Well, that's just counting. I hope we all know how to count to 4. Anybody believe they forgot how to count to 4? 1, 2, 3, 4. I just moved the vertex. Oh, genius, isn't it? And then I'm going to take 2 other spots, probably something out here. 1, 2, 3, 4, and something out here. 1, 2, 3, 4, to give me something to aim at. That is the graph of y equals the absolute value of x minus 4. Seriously? That's all we do? That's all we do. Look at the bullets. First bullet says, make a table. Did I make a table? We don't need no stinking tables. Cross that off of there. Tables. We don't need no stinking tables. We're going to graph it. It's easy. You just graph y equals the absolute value of x and you move it. That's all you do. According to those transformations we did yesterday. That's what we do when there's a number in here with the x or there's a number behind. We're going to see what happens with our stretches and compressions later today. But for right now, we're just moving this baby. That's all we're doing. And it's counting. That's all we have to do. So, next slide. What is the graph of the function y equals the absolute value of x plus 2? That's not where I start. I start with my parent function. 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and equal but opposite on the other side. Not solid, dashed or dotted. And then I say, I don't need a table. All I need to know is what that 2 is going to do. What is that 2 going to do? We count. Up 2. And we aim. See what I told you? We might forget this because it's too easy. Yeah. It does change in a little bit, so we will have a little bit more to think about. But if we just see when it's y equals a, absolute value of x minus h plus k, if there's no change to this, it is this easy. So as long as a stays a 1, this is the process we use. And when it says, how is it different? We write translate, translated 2 units up. That's how it's different. So the way that we think about it as we go to graph it is what we described. Absolute value of x moved. So now, this asks us a really general question. It says, what we just did was we looked at this k back here. Did that affect the axis of symmetry? Well, look at the last two. No? Still the y-axis, wasn't it? Yeah, so the axis of symmetry, oh, that's not a y. The axis of symmetry is still x equals 0. Remember, that's our equation for the y-axis. I get the feeling they want us to think about that a little bit. So when we moved it up and down, axis of symmetry didn't change. We know what's coming, right and left. Is the axis of symmetry going to change if we move it right and left? Yeah, it's not going to be the y-axis anymore. So they're getting us to start thinking it doesn't make a difference for the axis of symmetry if you move up and down, but it definitely makes a difference if we move it side to side. Our horizontal movements, our x movements. So let's see what all these transformations are going to do for us here. Turns out all the good stuff we learned in 2-6 going to work here too. When we did that section, I said if we do this right, we get this down now, we're going to be able to use this again and again and again this year. And we're going to be so happy that we know how to do it. We just saw an example of that, where we were able to graph really quickly and really easily because we know about k. So now this says, if you have a number bigger than 0 in this spot and you add it, you're going to move it up. And for this one, if you have a k value bigger than 0, but you're subtracting it, you're moving it down. Here's where it gets weird, remember. If it's inside the absolute value, you have to think backwards. So if you see a minus, it actually goes to the right. And if you see a plus, it actually goes to the left. We saw that with the graphic calculator the other day. Then it says, we're going to give you an a value in front. Now that kind of messes up our system a little bit, but not. So hang in there. If a is bigger than 1, we have ourselves a vertical stretch. If a is a fraction between 0 and 1, we have a vertical compression. Same thing we didn't do since. Reflections. This first one is going to be a little hinky. It says reflect in the x-axis. We already know that that means we're supposed to slap a negative in front of the y. But we also know we don't leave it that way. We always want y by itself. So we'll divide by -1. And that is where they got their little answer from. It seems to come out of nowhere, and I didn't want to just say, hey, look at that. You know, that's what we do. We think our way through it and say if you're reflecting the x-axis, you need a negative in front of the y. Oh, wait a minute, I can't leave that. I've got to divide it by a -1. So that's where that came from. Reflection in the y-axis, quite frankly, at Algebra 2, we're not going to talk a lot about reflecting over the y-axis. This is more for pre-calc right here with that negative in front. Can it happen? Yes. Do we know how it happens? Absolutely. If you reflect in the y-axis, you make the x negative. But because we now have a negative in front of the absolute value, things can get a little hinky. So that's why we don't necessarily use that one lot in Algebra 2. So down here, we have multiple choice. Hooray! We have a 25% chance of getting it right if we know nothing. But we do know stuff. We know this formula. And the reason I write that formula down is so we don't mess up on the x. That's where people make mistakes. So let's see. I could make my normal graph, but then I'm going to have to move it. And if I'm going to have to move it, my vertex will move. So my vertex right now is at 0, 0, but this is telling me to move it which way? So it'll be a -2. And this is telling me to move it which way? Up 3. There's my new vertex. Which one of these has a vertex? It's the only one. That's our absolute value graph right there. That's what we needed. So, H and K, not too bad. Here's our got it. It says, what's the graph of the function y equals the absolute value of x minus 2 plus 1? I see that a is still 1, so I tell myself, graph the parent function, self. Do the usual v business. A dash. That's all. That's our helper. Because what we need to do is figure out how we're supposed to move that bad boy. That's fine. So now we go back up there. And we think, if it looks like this inside these parentheses, where am I supposed to go? I guess I should say inside these absolute value bars, not parentheses. 2 to the right. Plus 1 in the back. What does that do for us? Up 1. So, a couple of things I can do. Obviously, I could just count, take my vertex and go 2 to the right and up 1. I'll have my new spot. Then we can move 2 more points and connect them up. But let's try something a little different, where we say our new vertex is going to be at 2, 1. And I know the slope of the right branch is 1. So I can go up 1 and over 1, up 1 and over 1. And the slope of the left is the opposite of that. So up 1 and back 1, up 1 and back 1. Now I change gears because we are going to have some a values in front of this. And what we need to use is the fact that when it's not there, it's a 1. So the slope of the right side is 1. But if there is a different number up there, then the slope of the right side has changed. So if they throw a 1/3 up here, then the slope of the right side is up 1 and over 3. If they throw 5 up there, we'll go up 5 and over 1. So as long as we can find this vertex, we'll have a starting spot for all of these. And that's what we need that for. So now we see A. We're going to describe those transformations that we know come from the number that's in front. We talked about these yesterday. What happens to a graph if you multiply by a number bigger than 1, and what happens to a graph if you multiply by a number between 0 and 1. So what's going to happen to our parent function if that 3 is in front of it? You remember from yesterday. Yesterday was too long. And oh, vertical stretch. Carson, was that you? Vertical stretch. Factor of 3. Beautiful. Remember? Rubber band. Pull it. Top and bottom. Stretch it out. Oh. Okay. Carson just told me this is a vertical stretch factor 3. I'm going to write that down. Vertical stretch factor of 3. What did that do? The negative there. What's it going to do? Reflects it over the x-axis. Good. Reflect over the x-axis. Hey, won't that one point down? Yeah, Taylor was graphing that in the air. Uh-oh. Still there. What's that going to do? Good. Vertical compression. Factor of 1/3. Squishing it. That makes perfect sense if you think about slope. This one's going to be skinnier because instead of going up 1 and over 1, we're going to go up 3 and over 1. This one's going to go down 3 and over 1. Oh, that'll make it perfect. It'll go down. This one's going to go up 1 and over 3. Yeah, that's going to stretch it. That's going to hold it down. So when we get to problem 3, we're not going to put our parent on there anymore because our parent shape has been changed by this 1/2. It's now going to be compressed. So instead what we do is we look around for an H and K and we realize there aren't any. So this graph is going to start at 0, 0. And we use the 1/2 as the slope of the right side. So from our 0, 0, we're going to go up 1 and over 2. And then for the left side, you can either count and use symmetry. For instance, this one you could say, hey, this is 2 units away from the y-axis. I've got to go 2 units back here because it always has to be equal but opposite. This one's 4 units, 1, 2, 3, 4, 4 on the other side. Connect it up. Done. All we did was change the slope. That's all we did. So the slope of the left side ends up being a negative 1/2. Because we go up 1, but left 2. In fact, let me write it with the negative on the bottom. Maybe that'll make more sense in your notes. Up 1 and left 2. You get that? So, positive slope on the right side, negative slope on the left. Let's look at A. Does A have a new H and K? Are we supposed to move this right, left, up, down? No. There's no numbers inside the absolute value. There's no number hanging out in back. This is 0, 0 again. But what do I use for a slope of the right side? 2 over 1. So up 2 and the right 1 a couple times. Again, use symmetry or use a negative 2 slope. Go up 2 and left 1. But get a few points on there, enough to give you a nice V shape. Looks like so. Ooh, look at me. Ugly. Starting at someplace new, or are we still at 0, 0? Yep, no H and K. 0, 0. Well, what's the slope of the right side? Down 2 and over 3. Hey, wait a minute. That's going to make it up and down. What was it supposed to? It has a negative. It was supposed to. And down it goes. Ta-da! 4, 3, 2, 1, 0. How do you feel? After absolute values. Okay, 4s and 3s. Good numbers. Good numbers. All right. So, you need some practice. That's what it is. You need some practice. And it will definitely take longer to make your Cartesian coordinate plane than it does to graph these. So I know some of you don't like using graph paper, but you might want to make an exception this time. Maybe staple it to your paper right now if you're worried you're going to lose it. But it'll take you longer to make your Cartesian coordinate plane and put intervals on it than it does to graph.